Okay, I want you to close your eyes for a second. I want you to picture yourself on a street corner in central Hong Kong, Devo Road, but not on a nice sunny day. Imagine you're standing there during a T8 signal typhoon.
Which, if you haven't experienced it, is just a visceral, full body experience. The pressure drops, your ears pop, the sound alone is deafening.
It is. The wind howls through these, concrete canyons. And the rain, it isn't just falling down, it's coming in sideways, these huge, heavy sheets of water. You look up and you're just surrounded by these glass monoliths disappearing into the mist.
It makes you feel incredibly small, a real reminder of nature's power, even in the most man-made place on Earth.
Exactly. You feel tiny. And normally, when we're standing there getting completely soaked, we see all that water as a problem, a huge problem.
And hazard.
It floods the MTR, it ruins your shoes, shuts down the stock market.
It's a total logistical nightmare. In urban planning, we talk about stormwater as something to fight. You build drains, you build canals, you try to get it out of sight as fast as you possibly can.
But today, we are going to completely flip that script. This deep dive is based on some research that asks a really radical question. What if the violent storm combined with those giant skyscrapers is actually a giant battery just waiting to be plugged in?
And that is really the core mission for us today. We're looking at this fascinating paradox in Hong Kong. You've got one of the wettest cities in the Pacific Rim. We're talking over 2,400 millimeters of rain a year.
Which is just a staggering amount of water.
Staggering. And at the same time, you have arguably the most vertical city on the planet.
And yet, with all that wind, all that rain, all this amazing engineering, Hong Kong really struggles with renewable energy.
It's a massive challenge. I mean, the city has basically zero ground space for solar farms. Land is just far too expensive, and it's way too dense for traditional wind farms.
But there's this new wave of research, a lot of it coming out of the City University of Hong Kong, that suggests the city's biggest constraints, the overcrowding, the shadows, the storms, might actually be its biggest energy assets.
We're talking about rain energy harvesting.
And I just want to set the expectation right now. We are not talking about putting like little plastic water wheels in the gutter to power a flashlight. This is about turning the skyscrapers themselves into massive power plants.
Specifically, a breakthrough technology called the droplet-based electricity generator, or DEG for short.
The real aha moment for me, reading through all this, was so simple, kind of broke my brain a little. We've been completely obsessed with putting solar panels on roofs.
Rooftop solar, yeah.
But in a place like Hong Kong, we've been ignoring the walls.
And that's the vertical jungle theory. When you run out of horizontal space, which Hong Kong did, decades ago, you have to start harvesting the vertical.
So let's unpack that. Before we get into the sci-fi tech of making power from raindrops, we need to understand why the usual suspects, solar and wind, have such a hard time in Hong Kong.
Right.
I mean, it's a subtropical city. It's hot. It's sunny a lot of the time. Why can't we just plaster solar panels everywhere?
You would think so. If this were, say, Arizona, that would be the plan. But Hong Kong's geography it's very specific and very aggressive. And it creates what urban planners call the urban canyon effect.
The urban canyon. It sounds like something from an action movie, but it's a real physics problem.
Yeah. It's very real. When you have buildings that are 50, 60, even 80 stories tall, packed so tightly together, the sunlight just doesn't reach the bottom.
Yeah, I walked through Mong Kok at noon, and it can feel like twilight because the shadows are just so deep.
Exactly. And that really matters for solar. Panels need direct sunlight, direct hits to be efficient. If you're in shadow or you're just getting scattered light bouncing off other buildings, your efficiency just drops off a cliff.
By how much?
We're talking drops of 50, 60% or even more.
So you can't put them on the street, you can't put them on the walls because they're in shadow. So what about the roofs? The skyscrapers have roofs.
Well, think about a Hong Kong skyscraper roof. In a sprawling city like LA, you have acres of flat warehouse roofs. In Hong Kong, the roof is a tiny postage stamp compared to the height of the building. They're like needles.
And I'm guessing it's not empty space up there.
Not at all. It's prime real estate for all the mechanicals. You've got HVAC chillers, water tanks, elevator motors, window washing rigs, maybe a helipad, a sky garden.
So the roof is already spoken for.
It's finite and it's full, so solar is fighting a losing battle for space.
Okay, so solar's out. What about wind? If we started this talking about typhoons, incredible wind, why not stick a turbine on the side of a building?
That's even trickier. It all comes down to fluid dynamics, specifically turbulence and vortex shedding.
Vortex shedding. Okay, now we're getting technical. Break that down.
A wind turbine wants clean air, a smooth laminar flow, like wind over an ocean. But when wind hits a square building, it doesn't flow smoothly around it. It breaks up. It creates these chaotic swirls and eddies on the other side. That's the vortex.
So it's just messy air.
Incredibly violent, messy air. And if you put a standard turbine in that, well, the constant chaotic shifts in wind direction and speed create uneven torque. It would literally tear the gears to shreds.
You'd spend more on maintenance than you'd ever make in electricity.
Pretty much.
So the sun's blocked and the wind is too chaotic. It feels like we're running out of options.
Which brings us to what the research calls the suitability matrix. It's a way of looking at what the city actually allows you to do. Solar needs land or big roofs. Wind needs open space. But rain
doesn't care about shadows.
Rain is immune to shadows.
Right.
And more importantly, rain harvesting has a low space requirement because you can integrate it directly into the facades, the walls, which is the one thing Hong Kong has in absolute abundance.
Okay, so that sets the stage. We need a power source that loves vertical surfaces and doesn't mind a storm. Enter this droplet-based electricity generator from City U.
This is really the star of the show. It's a genuine paradigm shift in how we think about hydro energy.
I have to admit, when I first heard rain energy, I was picturing like a tiny hydroelectric dam on a windowsill. But this is molecular science.
It is. The old tech was called triboelectric, which was basically just using friction.
Like rubbing a balloon on your hair to make static electricity.
Exactly that principle. And it was about as efficient as you'd imagine. It made tiny sparks. A novelty. The breakthrough here is a new structure based on a field effect transistor, or FET.
Okay, let's slow this down. Let's really get into the nuts and bolts. How does a single drop of water hitting a piece of glass create any meaningful amount of electricity?
It's a brilliant three-step process. So step one is the material. Imagine a glass surface coated in a very thin layer of PTFE.
PTFE, that's Teflon, right? Like a nonstick pan.
Yes, chemically very similar. And Teflon has this ability to store a quasi-permanent electric charge. So as rain hits it and flows over it, the surface itself builds up a high density of static charge. Think of it like charging a battery, but the battery is the surface.
Okay, so the Teflon layer is just holding on to this charge like a loaded spring, waiting for a trigger.
Exactly. Step two is the bridge effect. This is the genius part. Embedded in the device are two electrodes, one made of aluminum, one of indium tin oxide, and normally they aren't connected, it's an open circuit.
The switch is off.
Correct. But when a raindrop hits that surface, it spreads out. And for a split second, that water physically touches both electrodes at the same time.
The water becomes the wire.
The water becomes the bridge. It closes the loop. Which leads to step three, the release. Because the circuit is now complete, all that charge stored in the Teflon layer is released instantly in one massive pulse.
I love that. The drop hits, spreads, and zap it just dumps all the energy. It's not a trickle, it's a dump. And the numbers here are they're wild. The source says one single droplet, a tiny amount, 100 microliters, can generate 140 volts.
It's astonishing. 140 volts is significant. It's enough to momentarily light up 100 small LED bulbs.
That's the visualization that just stuck with me. One drop, 100 lights.
It really changes how you see a storm, doesn't it? Instead of just wet, you start seeing millions of these potential electrical pulses hitting the city every second. They achieved a peak power density of 50.1 watts per square meter.
Which puts it in the same league as solar panels, doesn't it?
In terms of peak output during a storm, absolutely. It's competitive. Which, of course, brings us to the big question, does this actually scale?
Right. Lighting up LEDs in a lab is cool, but can it power a building?
Can it run the elevators? And that's where the ICC case study comes in.
This is my favorite part of the research. I love a good theoretical showdown.
So the International Commerce Center, the ICC.
For anyone who hasn't seen it, it's the tallest building in Hong Kong.
Yeah.
484 meters tall. It's an absolute beast of a skyscraper. And the researchers basically ran a simulation. What if we covered the ICC in this rain harvesting scan?
And this is where that geometry argument we talked about earlier really pays off. The roof of the ICC, it's about 3,800 square meters.
Sounds big, almost an acre.
It is big. But then you look at the facade, the glass walls. That area is roughly 50,000 square meters.
So the walls are more than 13 times larger than the roof.
Effectively, it can be up to 50 times larger when you consider the usable surface area. You aren't losing space to HVAC units on the walls. It's massive. This is the negative space argument. If you only look at the roof, you're ignoring what? 98% of the building's wet surface.
So they ran the numbers. What happens during a storm?
Well, this is the reveal. Let's take the roof first. If it's covered in solar panels during a heavy storm, your output is 1.
0. It's dark and raining.
Close to 0. But let's be generous. Let's say we look at its peak capacity on a perfect sunny day. That roof can generate about 0.76 megawatts.
Okay, 0.76 megawatts for the roof. That's the baseline.
Now, you take that rain harvesting skin on the 50,000 square meter facade. During that same heavy storm, the output hits roughly 2.5 megawatts.
Oh, wait. So in a storm, the walls are generating more than 3 times the power that the roof could ever generate, even on a perfect sunny day.
Precisely. You're just working with a much, much larger canvas. Rain lets you use the building scale in a way that solar just can't.
That is staggering. It completely flips the narrative. The storm isn't the downtime for the grid, it's the surge time.
It's the high yield event, and that's just the kinetic energy of the drops hitting the glass. There's a whole second layer to this research that I think is even more practical right now.
You're talking about the virtual dam.
Exactly. Think about what happens to the water after it hits the window. It doesn't just disappear. It runs down, it goes into gutters, and then into these huge vertical drainage pipes.
And gravity takes over.
Right. A 50-story building is, in essence, a hydroelectric dam. You have all this water at the top, and it's falling hundreds of meters to the bottom. That water inside the pipes has immense potential energy.
So instead of just letting it crash into the sewer, you put turbines inside the pipes.
Microturbines. You can put small, inline turbines inside the building's plumbing. The research calls it turning a sunk cost, the drainage you have to build anyway, into a revenue stream.
That just makes so much sense. You have to build the pipes to stop the building from flooding. You might as well stick a generator in there.
And Hong Kong is uniquely positioned for this because it's already a sponge city.
Right, the sponge city. I've heard that term. It means the city is designed to absorb and hold water, not just repel it.
Exactly. Because of its history with flooding, Hong Kong has some of the most advanced flood infrastructure in the world. There are these huge underground caverns for stormwater storage, like the one under the Happy Valley Racecourse.
And the vision here is to integrate power generation into that existing flow of water.
Yes. If you're already moving millions of liters of water into a holding tank, that is energy you are currently just wasting. The Hydrometropolis vision sees every pipe, every gutter as a potential power source.
It really paints a picture of a city that lives with water instead of fighting it. But I have to play devil's advocate here for a second.
Please bring me back down to earth.
It doesn't rain every day, even in Hong Kong. We have a dry season. Solar works pretty much every day, at least a little bit. Isn't rain energy just unreliable?
That is the most common criticism. What about the dry days? And it's a valid point. You can't run a city on rain alone. But the researchers address this with a concept they call hybrid resilience.
Hybrid resilience. What does that mean here?
It means you don't choose one or the other. You look at when they peak. So they plotted the energy output over a year. Solar is great in the winter when it's dry and clear. But in the summer, during typhoon season, solar production just plummets.
Because of the clouds and the rain?
Right. There's this massive solar gap, and guess what fills that gap perfectly?
The energy.
Rain energy. It peaks exactly when solar fails. They are perfectly complementary. It's like a relay team. When the sun gets tired, the rain takes the baton.
So it's not about replacing solar. It's about filling the holes in the grid during bad weather.
Exactly. It's the stabilizer. It flattens the curve.
I love that. So let's look forward. What does this future actually look like? If we fast forward, say, 20 years and this tech matures, what do I see on the street in Hong Kong?
The sources describe this really cool vision of the Hydrometropolis. Imagine smart windows. The glass on the skyscrapers isn't just glass anymore. It's a transparent DEG film. And it's powering the sensors inside the office that control the lights or the AC.
The building skin is powering the building brain.
Yes, a self-sustaining loop. And at street level, bus shelters, umbrellas. The research explicitly mentions coating umbrellas in this material.
Wait, my umbrella?
Your umbrella. Imagine you're walking in a downpour and the rain hitting your canopy is charging your phone in your pocket.
That would actually make me look forward to a rainy commute.
And think about infrastructure. Bus stops lighting up their own schedules just from the rain falling on their roofs. It decentralizes power. You don't need to dig up a road to lay a cable for a sign if the sign powers itself from the weather.
So we aren't there yet. What's holding it back? Why isn't the ICC covered in this stuff today?
The roadmap in the source material highlights a few big hurdles. The main one is durability.
Let me guess. The salt.
The salt. Hong Kong is a coastal city. The air is salty, it's humid, it eats metal. creating a delicate nano generator that can survive a 100-mile-an-hour typhoon and 10 years of corrosive air. That's a huge materials science challenge.
It's one thing to work in a lab, another to work on the side of a building in a hurricane.
Exactly. And then there's the storage issue. The energy comes in these quick pulses, zap, zap, zap. Our grid doesn't like that. It likes a steady flow. So you need to integrate supercapacitors to smooth those bursts into a steady current.
So better batteries and tougher materials. But the physics works.
The physics works beautifully. And the economics of using waste space on walls, it's incredibly compelling. The land cost is zero. The wall is already there.
It really just brings us right back to that intro image, standing in the storm.
It does.
We spend so much time talking about how cities need to be greener. And usually that just means, planting some trees. But this feels different. This feels like the city itself is evolving.
That's a great way to put it. In nature, nothing is wasted. A rainforest captures every single drop of water. This is just suggesting that our concrete jungle should do the same thing.
It's about finally harnessing the verticality.
It is. We've built these mountains of glass and steel. We created these canyons. Now we're just finally realizing that the weather passing through them is a resource, not a nuisance.
So here's my final thought for you listening. The next time you're stuck inside during a downpour, looking out at the gray sky, maybe you don't just see a gloomy day.
Right.
Look at the building across the street. Think about the millions of gallons of water cascading down its side. That is a massive untapped waterfall right in the middle of the city. Wow. Just haven't plugged into it yet.
And when we do, the skyline won't just be a place where people work. It will be the generator that keeps the lights on.
I'll never look at a rainstorm the same way again. Thanks for taking this deep dive with us.
It's been a pleasure. Stay dry out there.
See you next time.